For problem 3, we have a piston cylinder device that contains air, stops, and a linear spring as shown in the figure below. Air initially occupies a volume of 0.5 cubic meters at an absolute temperature of 1000 Kelvin when the spring is touching the piston without exerting any force. Air is cooled until the piston hits the stops when the volume of the air is 0.2 meters cubed at state 2, and then further cooling of the air decreases the absolute temperature of air to 250 Kelvin at state 3. The mass of the piston is 20 kilograms, its cross-sectional area is 0.03 square meters, and the spring constant is 100 newtons per meter. Okay, so this is another longer multi-part problem. So I'm going to take some time again to set up the problem here. Feel free to stick around if you want to watch, or you can skip ahead to the solution. But I'll start just setting up the problem. And so they want us to, again, draw out our system in an energy flow diagram here, and then to make some assumptions and write down our basic equations here. So we'll start with identifying the system. And actually what's happening here before we get into the system is we have this piston, we have another piston cylinder device. This piston has some weight this time, it tells us. And so this piston is going to try to fall down. And then this spring is initially not in compression. It says the spring is touching the piston but not exerting any force. So it's just sitting there at state 1. But then as this piston falls, the spring will push back against it and compress. And then there's air inside of this piston cylinder device, which will also press against the piston as it falls. And there's also atmospheric pressure that is pushing down on the other side. So part A is asking us to draw a free body diagram for the piston, and we'll have to worry about all those forces then. But for now, let's set up the system. So first we have to choose our system here, and there's actually a few different options. What I think makes sense here is to choose the system as just the air inside this piston cylinder device. So I'm going to write that our system here is just going to be the air inside the cylinder. Another logical choice would be to choose the air in the cylinder and the spring. You could include the spring as part of your system since it is inside of the cylinder here. But for me, I just want to focus on the air that's inside of here and not touch the spring. Because if we include the spring in our system, then we have to worry about the changes in energy of the spring as part of the changes in energy of our system. So as the spring compresses, its energy is going to change, and then the energy of our system is going to change. But if we just choose the air, then we don't have to worry about the changes in energy of the spring for our system. And another thing is that the spring doesn't really interact with the air at all. The spring is just interacting with the piston here. So we'll worry about that in our free body diagram, but it doesn't really interact with the air at all. So I'm just going to choose the system as the air inside the cylinder. And then for this problem statement, this one is definitely a bit longer than our problem statement for question 2. So I think in this case, it makes a lot of sense to create a table, which I have just kind of sketched out here to the right, because we're given a lot of different properties at different states. We have 3 different states that we need to keep track of. So this will help us stay organized. So the first thing that I see from the problem statement is that it gives us some information about the volume, the total volume. At state 1, it says it's 0.5 meters cubed. So I'm going to make a column for volume in meters cubed. And so at state 1, it's 0.5 meters cubed. And then it tells us that it drops to 0.2 meters cubed at state 2. And you might think it doesn't give us any information about the volume at state 3, but actually we need to read the problem just a bit closer, because it's saying that the piston is hitting the stops at state 2, which are these black little blocks here. And so once it hits these stops, the volume can't change anymore. So the piston is going to fall, and it's going to end up at some spot right here, just resting on top of these stops. And the volume that we have here at state 2 is going to be the same as the volume at state 3, because the piston can't go any further. And as we cool, it's going to want to go down further, but since it's hitting the stops here, it's not going to be able to. So this amount of volume that we have at state 2 is going to be the same as the volume at state 3. So we can just write that as well. It's going to be equal to 0.2 at state 3. Okay, the next thing that I see from the problem statement is that we're given some information about temperature at state 1. So I will make a column for temperature in Kelvin. And so we have a temperature of 1000 Kelvin for the air at state 1. And then we don't have any information about the temperature at state 2, but then at state 3, it is cooled even more to 250 Kelvin. Okay, and that's about all that it gives us for now, but I'll leave some room in our table so that we can keep track of some properties later on. So now we'll move on to assumptions. And remember, we had a piston cylinder problem just last problem, so let's try to remember the assumptions that we made there and see if they apply here. So one of the ones we made last time is that we had a quasi-equilibrium process. And that's a pretty good assumption for most piston cylinder problems. Because what that means for us is when we're given a temperature of 1000 Kelvin at state 1, you might say, where are you talking about inside your piston cylinder device? Are you talking about the temperature right here or right here? But quasi-equilibrium means that the temperature right here is the same as it is right here. And the temperature is just uniform throughout. So we're able to just report one value for temperature. And the same thing happens when we move to states 2 and state 3. When we have a different volume now, we can still say that the property right here is the same as the property here and here and here and all over. We have the same uniform property and we can just report one value for it. So quasi-equilibrium process is going to apply here again. And then another one that we made last time was that as this piston moves down, it's not rubbing against the walls. They don't give us any information about any friction coefficient or anything like that. So we can just neglect the friction between the piston and the cylinder. So I will write neglect friction. And then for this one, for last one we had some sort of water substance, but for this one it tells us that we have air inside the cylinder. So pretty much anytime we have air, we're going to want to assume that air is an ideal gas, which will allow us to use the different equations and relationships that we have for ideal gases. So since we're given air inside the cylinder this time, I'm going to assume that air is an ideal gas. And then one more thing that I see is that we should assume that we have a closed system. So there's no mass coming in or out of this piston cylinder device. The amount of mass in here is going to be constant the entire time. So this system is going to be closed. We don't have any inlets or outlets or anything like that. So I will just write that this is a closed system, which means that the mass is going to be constant. And then, whoops, I forgot to actually draw my arrows for the energy flow diagram. So I talked about what's going on with the system, but we need to actually draw on the schematic here our arrows for heat transfer and work and figure out how is this air interacting with its surroundings. So for heat transfer, it's telling us that this air is being cooled, which means that we needed to take some heat out of the system in order to cool the air. So I'm going to draw my Q for heat transfer going out of the system here. And then for work, we also know that at some point this piston is going to be hitting the stops, which means that it's going to be moving downwards and finish at a state down here. And in order to do that, it needs to do some work on the fluid here. So the piston will be doing some work on the air inside the cylinder. And so I'm going to draw my W arrow pointing in to say that there's going to be some work being done on the system. And that's all we have for our energy flow diagram. So now we can move on to our solution for part A. Now we can move on to our solution for part A, which asks us to draw a free body diagram for the piston showing appropriate forces at state 1 and to calculate the absolute pressure of air at state 1 and report our answer in kilopascals. So we want to draw a free body diagram of this piston here, and in order to do that, we need to figure out what forces are acting on the piston. So it tells us that we have some mass of the piston here, and since this is oriented in the vertical direction, we know that anything with mass will have some gravitational force that points downwards here, so we'll want to include that. And we also see some information about atmospheric pressure on the outside of this piston cylinder device. So this pressure will be acting downwards on the face of the piston. It will be distributed all along the top face here, and that will result in a net negative force that points downwards. And similarly, the air inside the piston cylinder device has some pressure, so it will exert a pressure on the bottom face of the piston all along here, which will result in a positive net force upwards. Now, what about the spring force here? I see a spring, so do we have any spring force? Well, we need to be really careful because it's asking us to figure out what's happening at state 1. And the problem tells us that at state 1, the spring is touching the piston without exerting any force. So it's touching the piston here, but it's not exerting any force on it. It's just kind of chilling there. So we don't want to include that force of the spring in our free body diagram, so we'll only have the 3 that we just discussed. So let's draw our free body diagram down here in the solution. So like we said, we will have some weight of the piston that acts downwards. So I'll just draw that as WP, and that will be equal to the mass of the piston times our gravitational constant. And then we have the other 2 forces in terms of pressure, but we want to express those as forces, not pressures. So we need to remember that pressure is equal to a force per area. That's just our definition for pressure. So if we want to get this and express it as a force, we just say that the force is equal to the pressure times the area over which it acts. So for this atmospheric pressure, for instance, it gives us a value for the pressure, and the area over which it acts will just be the area of the piston here, this 0.03 meters squared. And the gas, we need to figure out what the value of the pressure is, but it will also act over the same area of the piston just on the bottom of it. So then let's draw those in. So we will have a net force from the atmospheric pressure that will just be equal to P atmospheric times the area of the piston. And then on the bottom, pointing upwards, we will have a pressure from the gas at state 1 times the area of the piston that is acting upwards. I'll move these over a little bit. Okay, those are all the forces we have. Remember, we don't have any spring force because it's just touching the piston. So then we can write out our summation of forces. And there's only one direction in which the forces act. So we'll denote positive as upwards. So we'll have a positive P1 times AP minus a atmospheric pressure times AP and minus the weight of the piston, MP times G here. That points downwards as well. So what should we set these equal to? Well, we need to understand that at state 1, this is before the piston has begun moving yet. It's in an equilibrium state before it has begun its motion downwards. And so we're just going to set this equal to 0 because we're assuming that it's not accelerating yet. It's just still in state 1 before the process of the movement starts. So we are going to set this equal to 0. And then we want to solve for P1 here so we can rewrite this equation. We have everything else known. They give us a value for AP. They give us a value for the mass of the piston. They give us the atmospheric pressure, and we know gravity as well. So we could just rearrange this equation and solve for P1. So we can say P1 times AP is equal to, moving the other terms to the other side, P atmospheric times AP plus the mass of the piston times the gravitational constant. And then we can just rearrange by dividing both sides by the area of the piston, and we will get the final version of this equation here, dividing everything by the area of the piston. Then we can just plug in our values. So it tells us that the atmospheric pressure is 1 bar, which, just remember, you can check your equation sheet if you forgot, but that's just equal to 10 to the 5 pascals. And they tell us the area of the piston is 0.03 meters squared, and the mass is 20 kilograms. So we can plug all those values in. Again, for P atmospheric, we have 10 to the 5 pascals. And then the area of the piston is 0.03 meters squared, plus the mass of the piston is 20 kilograms. And gravity, we can use 9.81 meters per second squared, divided again by the area of the piston, which is 0.03 meters squared. So if you plug that all into your calculator, you should get P1 is equal to 106,540 pascals. But remember, it asks for our answer in kilopascals, so we can just say that P1 is equal to 107 kilopascals. And this will be our final answer here for part A. Now let's move on to our solution for part B, which asks us to determine the displacement of the piston corresponding to the volume change from state 1 to state 2, and to report our answer in meters. So when I first read displacement of the piston, my brain immediately went to thinking about the spring, because we know that the equations for the spring, like the force and the work equations of the spring, include delta x, which is just this displacement of the piston that we care about. So that's the first thing that I thought about, but actually there's a much easier way to do it. You probably can use the spring to do it, but they give us a hint in the problem about the volume change from state 1 to state 2. So I think it's a good idea to use that volume change in order to find our delta x. And there's a way to do it, and I think the best way to think about it is in 3 dimensions. So I will attempt to draw things out in 3 dimensions without confusing you. But here I have just sketched our empty cylinder device whenever the piston is at the top here. So I'm just assuming that the piston is at the top and it hasn't moved yet, which is what we have at state 1 when the piston is up here. So this volume that we have inside here is the same as this black volume that I've drawn out here. So I'm going to denote this as our volume at state 1. And then at a later time, or at state 2, our piston moves down here, right on top of the stops that I've drawn here. And so the new volume under it, under this piston, is going to be this shaded region here. And that's going to be equal to this volume in the 2-dimensional sketch, which is just the volume that we have at states 2 and 3. And so we can sketch that out in a different color here. So I'll just sketch this volume out in blue. And this is going to be our volume at state 2 or state 3. And so if we look at the change in volume, it's going to be just the difference of these two, which is just the cylinder above this blue cylinder segment. And so it's going to look something like this. And this red volume that I'm drawing is just the change in volume, which we can just write as V1 minus V2. Right, because V1 is the black volume, which is on the outside here. So that black volume minus this blue volume here just gives us this red volume. And we can also remember that the delta x should be this length here, this amount that the piston has been displaced. And so we can remember that we can write this volume in another way. This red volume is going to be equal to the area of the piston times this delta x value down here. And that just comes from our equation for the volume of a cylinder. If you remember from a geometry or calculus class, we usually write that as pi r squared times L, if these being the dimensions of the cylinder, but this pi r squared, that's just our area of the piston, just the area of this face here. And then our length, since this is just a chopped segment of the cylinder, this is the length that we care about, this delta x. So that will be our length value for this red block of volume here. So all we have to do is equate these two equations together, and the math is actually really simple. It's just hard to figure out how to get there. But if we think about it like this in 3 dimensions, maybe it makes it a little bit easier. But we can just equate those two terms and say that the volume is equal to the area of the piston times our displacement delta x, and that's also equal to our volume at state 1 minus our volume at state 2 or state 3. And so just rearranging for delta x, we'll just get volume 1 minus the volume at state 2, all divided by the area of the piston, just moving that over to the other side. And then we have all these values. Just look back up to our table. We have our V1 and our V2, and then the area of the piston is also given here. So just plugging in our values, we'll get V1 is 0.5 meters cubed minus 0.2 meters cubed, all divided by the area of the piston, which is 0.03 meters squared. And just checking the units, this meter squared will cancel out with 2 of the meters from above, and we'll be left with an answer that is in meters. So that makes sense because we want our delta x to be in meters. So then we'll get delta x is just equal to 10 meters once we plug this into our calculator. So this is our final answer for part B. Now we can move on to part C. So we are asked here to draw a free body diagram for the piston showing appropriate forces at state 2 now, and to find the absolute pressure of the air at state 2 and report our answer in kilopascals. So we need to look at our schematic and figure out what forces we should include since we're drawing another free body diagram. But this schematic is getting a little bit messy here, so let's move down and draw a new schematic. And I've drawn this one now showing what the piston looks like at state 2. So now it's dropped down and it's sitting on top of these black stops here in the diagram. And remember, at first it was at state 1, which is up here, and now it's been displaced through some delta x that we found, and now it sits down here. So what are the forces acting on this piston now that it's at state 2? Well, we still have atmospheric pressure. Even though the piston has moved down, the atmosphere is still able to act on the piston here. So we're going to have some pressure along the top face of the piston due to the atmosphere, which will result in a net negative force downwards. And the gas inside the cylinder will still have some pressure as well, so it will push up on the bottom face of the piston, and that will result in a net force upwards. And the piston still has mass, so it will clearly still have some gravitational force that we should include. And then now we need to worry about the spring, because the spring is compressed now. When this piston drops, it compresses the spring, and so the spring wants to return to its equilibrium state, which is the length that it had when it was up here at state 1. So it will exert a force on the piston to try to return to its equilibrium state. So it will have an upward force on this piston. So that's all the forces we need to think about. So let's draw our free body diagram. Let's draw another rectangle here and label all of those forces. So we said we will still have some weight of the piston, which will just be equal to the mass of the piston times gravity. And then also a pressure force, due to the atmospheric pressure on the top face pointing down. So this will be a negative force. And then we'll have the pressure of the gas, but now it will be a different pressure, P2, and we'll multiply that times the area of the piston. And now we have to worry about the spring force as well. So I will draw an F spring pointing upwards. And remember that our equation for spring force is just the spring constant, Ks, times X, or delta X. And if you ever forget this equation for some reason, it's not given explicitly in the equation sheet, but here we do have the equation for the work of the spring. And remember from a physics class, we can sometimes write the work as the integral of force dotted with displacement. And so if we're talking about the work of the spring, then this would also be the force of the spring. So we can see that the force of the spring is actually inside the integral here. It's this K of the spring times the X. So that's our spring force if you ever forget. It's not explicitly in the equation sheet, but it's kind of hidden here in case you forget. And so these are all the forces we have, and now we can just write out a force balance. So we will say that the sum of the forces is equal to our positive forces are the ones that are going upwards. So we have a positive P2 times AP plus a positive spring force, which is Ks times the delta X value we found. And then these ones that are pointing downwards are going to be negative. So we have a negative mass of the piston times gravity and a negative P atmospheric times the area of the piston. Now, what do we set this equal to? Well, it's similar to the first part of the problem when we had to draw a free body diagram, where we have this piston that is now resting on these stops. So we're saying at state 2, it's not moving anymore and it's in equilibrium. It's not accelerating, so we're going to set these forces equal to 0. And we want to solve for P2. That's what the problem is asking us to do. So let's see, the area of the piston is known, the atmospheric pressure is known, the mass of the piston, gravity is known, the spring constant was given, and delta X we just found from the last part of the problem. So we have everything except P2, and we can just rearrange this equation for P2. So I'll just do it in one step here. P2 is going to be equal to the mass of the piston times gravity plus P atmospheric times the area of the piston minus Ks times delta X, because we're moving it over to the other side, all divided by the area of the piston. And then we can just plug in our values that we have. So the mass of the piston we were given is 20 kilograms, gravity 9.81 meters per second squared, plus P atmospheric, remember, is 10 to the 5 pascals, times the area of the piston, which is 0.03 meters squared, minus Ks was given in the problem as 100 newtons per meter. So we have 100 newtons per meter times delta X, again, we found is just 10 meters. All divided by the area of the piston, which is 0.03 meters squared. And so plug that all into your calculator. You should get that P2 is equal to 73.2 kilopascals. And so this will be our final answer for part C. Now let's move on to part D, which asks, what is the absolute pressure of air at state 3? And they want us to report our answer in kilopascals. So we're trying to find this value in our table right here, P3. And I've added in these values in red for pressure that we found from earlier parts of the problem. So remember, from part A we found P1, and part C we found P2. And those parts of the question were kind of leading us by telling us that we should draw a free body diagram. And that was helpful because we used the free body diagram in those cases to find the pressure. But for this part of the problem, they're not telling us to draw a free body diagram. So we should get the hint that we're not going to find the pressure through a free body diagram. We need to find a different way. And what is that way to find P3? Well, we need to remember that we are assuming that air is an ideal gas, which is helpful because we can use the ideal gas law. And remember, the ideal gas law is an equation that relates volume, temperature, pressure, and mass together. And look at our table, we have a lot of those values already. So we should kind of figure out that it's going to be convenient to use that equation. So let's scroll down to our equation sheet to look at the ideal gas law. Remember that this is our equation right here, PV equals mRT. And this R value is specific to the substance that you are examining. So for us, it's air. And so air, the R value, maybe you have it memorized, but if not, you can use this equation here to divide the universal gas constant by the molecular weight of air. And they give us this M value. And then R bar is found down here in the table, universal gas constant, there it is. So you can always calculate your R value for air if you don't have it memorized, but we'll go up to our equation section and write those down. Okay, so we have the ideal gas law, which is P times total volume is equal to mass times R of air, in this case, times the absolute temperature. And then we also have here that R is equal to R bar over the molecular weight of air. So that would be R of air. And molecular weight, remember, they give us right here. Okay, so this is all we need. So let's just start to write out this ideal gas law for state 3, because we want to find the pressure at state 3, so we need to relate all of the properties at state 3. So if we come down here and write that, then our pressure at state 3 times the total volume at state 3 is going to be equal to the mass at state 3 times R of air, which is a constant, and then T at state 3. So let's figure out what we know and what we want to know. So P3 is what we're trying to solve for. And then if we scroll up to our table, we have V3 and T3. But remember, V3, they didn't give us explicitly in the problem statement. We had to do some thinking to find it, and that was from when I was setting up the problem. So if you missed that, remember, they don't explicitly give us the volume in the problem statement, but what they tell us is that the piston hits the stops at state 2. So it's sitting right here, and then from state 2 to state 3, they're taking heat out. So if they were taking heat out, the piston would want to go down even further, but because it's sitting on these stops here, it's not able to go down any further. So this volume, which is the volume at state 2, is going to be the same at state 2 as it is at state 3. So, but we do have V3 and we have T3. So we have this, and we have R of air, we can calculate that. But what about M3? We don't have any information about M3. Again, we need to look at our assumptions and see that we are assuming that this is a closed system. And in a closed system, mass is going to be constant. So the mass at state 3 should be the same as the mass at state 2 and the same as mass at state 1. And if we look at our table, we have the values for volume, temperature, and pressure all at state 1. We found all of those values, and if we look at the ideal gas law, that means that we can solve for the mass at state 1 because we have everything else in the equation. So if we solve for the mass at state 1, then that's going to be equal to the mass at state 3, and then we'll have everything we need to solve for the pressure at state 3. So let's go ahead and do that. So just a quick note here, where you're going to write the ideal gas law for state 1. So P1 V1 is equal to M1 R of air times T1. And so if we rearrange this to solve for mass, we will get the mass at state 1 is equal to the pressure at state 1 times the volume at state 1, all divided by the R value for air times the temperature at state 1. Remember, for the ideal gas law, we want to use absolute values for pressure and temperature. So we want this to be in pascals or kilopascals, and then this should be in Kelvin instead of degrees Celsius or anything like that. So M1, if we plug in our values here, is going to be equal to P1 we found was 107 kilopascals. And times V1, which is 0.5 cubic meters. All divided by R of air, if you remember, is 0.287 kilojoules per kilogram Kelvin. So here I'm going to use this because the kilojoules will cancel with the kilopascals. But if you wanted to, you could also just use pascals and then joules per kilogram Kelvin. So then that would be 287 joules per kilogram Kelvin. So you can do it either way if you're remembering the value. And then T1 we have as 1000 Kelvin. So this is going to be equal to 0.186 kilograms. So now we have M1, and we need to say that M1 is equal to M3. And that lets us say that we can solve for P3 because we can plug this value that we got for M1 into our equation up here. So now we can just rearrange this equation and solve for P3, which is what the problem is asking us to do. So I will do that here. P3 is going to be equal to M3 times R of air times T3, all divided by V3. And so this will be equal to 0.186 kilograms times R of air. Let's do 0.287 kilojoules per kilogram Kelvin times T3, which, remember from the problem statement, tells us that it is 250 Kelvin at state 3. 250 Kelvin, all divided by the volume, which we were able to reason was 0.2 meters cubed. This is our equation, and then if you plug this all into your calculator, you should get a value for P3 around 66.8 kilopascals, depending how you do your rounding from other parts of the problem. But this will be our answer for the pressure at state 3. Now for part E, they want us to show the two processes on a PV diagram and to label the axes in the three states and to indicate the two process directions with arrows. So quick note here, this is a PV diagram that they're asking for with total volume, a capital V, but the PV diagrams that we're probably more accustomed to seeing are PV diagrams with a little v for specific volume. And usually when we draw these types of PV diagrams, they're in the SLVM range, and so we have some sort of saturation dome like this. But we need to remember that for this problem, we're dealing with air, and so we should be far away from this saturation dome. So we're not going to have one of these on our PV diagram. We're just going to have a diagram that's labeling the points for pressure and total volume and relating those points together. So if we look at our table, we already have all of the points for total volume and total pressure. We found those in earlier parts of the problem. So labeling the points here on the graph should be the easy parts, and then we need to figure out how they are connected. So let's scroll down to our diagram and start labeling those points. So we should have pressure on the vertical axis here like normal, and we'll label that in kilopascals. And then now we'll have total volume on the horizontal axis, so that will be in cubic meters instead of our specific volume, which is usually in meters cubed per kilogram. So now we just need to label our points on this graph first. So remember, P1 we can get from our chart here is 107 kilopascals, and V1 is 0.5 cubic meters. So we're at the highest volume and the highest pressure on our chart. And so we'll draw that point somewhere up and to the right so that we're at the highest point for both of those. We'll just draw it somewhere up here. This will be our state 1, and then we'll label the pressure at that state as 107 kilopascals, and then the total volume is 0.5 cubic meters. And then what happens at state 2, we drop to 0.2 cubic meters, and we drop in pressure as well to 73.2 kilopascals. So we're going to decrease in pressure, dropping downwards, and then decrease in total volume, dropping to the left here. So we can draw that point maybe somewhere around here. Again, it doesn't have to be perfectly exact. Just try your best and show the trends accurately. But we'll end up at a pressure of 73.2 kilopascals and then a total volume of 0.2 meters cubed. Now for point 3, remember we have this constant volume process in going from state 2 to state 3 because the piston is sitting here on top of the stops and it's not moving anymore. So the volume below the piston is the volume of the gas, and this volume will be constant for from state 2 to state 3. So we're still at 0.2 cubic meters. And on our graph, that just looks like a vertical line with this V value being constant. So this is called an isochoric process, and it will look something like this. So we can draw that in. We'll be at 0.2 cubic meters, and then pressure drops as well to 66.8. So we will drop in pressure to a point somewhere around here. This will be state 3. We will be at the same total volume value, but we'll be at a new pressure value of 66.8 kilopascals. So we can draw the arrow connecting point 2 to point 3 pretty easily because that's just a constant volume process. So this line has to be straight, and then this arrow will obviously point from 2 to 3. So that part's okay. But now connecting point 1 to point 2 I think is a bit more difficult. So I'll give you the answer first. It's just going to be a straight line from state 1 to state 2. It's going to be linear, and we'll draw our arrow obviously pointing like that. So this will be the final version of the PV diagram. This is the final answer. But if you're interested to see how I get this straight line, then you can stick around for the explanation. So to understand why this is a straight line from 1 to 2, we've done this a little bit before with free body diagrams in this exam, but if we can find some equation that relates pressure and volume, then that will give us the equation of a line. You know, for a normal graph, if you had like y equals x, then that would tell you that the shape of the line should be a straight linear line like that. So if we can find some relation between pressure and volume from state 1 to 2, then that will give us the shape of our line. So if we write that out, we want to find pressure from state 1 to 2 is equal to some constant stuff times the total volume. And I'll write v to the n here because that will help us see if we had n equals 1, for example, then that would be some sort of straight line like this because it would just be like writing, p is equal to v, which on our graph would be some straight line. And if it was anything greater than 1, like 2, then we would have some curvature to this line, because it would be like writing y equals x squared, which would be something like that. And so we want to find this equation from state 1 to 2. And the way that we can do that is remember that we had a free body diagram where we solved for this pressure at state 2 based on our free body diagram at state 2. So I'll scroll down to remind you of that work. So this was in part C that we did this. We had this FBD, and we were able to find this pressure P2 as a function of x. And x here, again, is just the displacement of the piston as it moves from state 1 to state 2. And the key thing to realize here, hopefully you can look at it and start to realize it. I mean, it's difficult to see, but as x changes, the total volume, this V, changes. You know, as this piston drops, the volume changes. But it's actually a linear relationship here because the area of this piston is constant. You know, the face of this piston, it's not changing at all. So the only way that the volume inside here changes is when x changes. And in this, you know, I just have this written out as h being this total height before the piston moves here. But you can see that volume changes linearly with x. So here we found in this equation that pressure changes with x like this. But really what that is telling us is that volume also changes linearly with x. And hopefully you can look at this and see it. You know, I can write out some work just to be a bit more thorough, but that's really what tells us that the line between 1 and 2 should be straight, because this pressure is a function of x to the 1, and you know, volume changes directly with that x value. But if you wanted to see the work for that, you know, I can just write this out to say V equals AP times H minus APX. And so if we rearrange this for x, we would get x is equal to, let's see here, the height minus volume over AP. And if we just plugged this x directly into our equation here, then we would see that it's, you know, pressure is equal to some constant stuff here times V to the 1. I guess I can do that if you really want to see, but pressure is equal to, oops, all of this stuff here times this H minus V over AP. And then once you distribute this K to the A, you get some pressure is equal to V to the 1 here. You know, on an exam, time is really limited, so you hopefully wouldn't want to write out all of this work here. Hopefully you'd be able to get it from seeing in this equation that pressure is directly related to x, and x here is directly related to volume. But that's the reason that we have a straight line, so hopefully that makes some sort of sense. But if you can see this, then you're on the right track, seeing this relationship between pressure and x and how x is related to volume down here. Now we can move on to the last part of the problem, which is part F, and that asks us to find the boundary work for air in the cylinder from state 1 to state 2 and to report our answer in kilojoules. So we need to make sure to read the problem carefully here, because they're not asking about the total work on the system, which is this arrow we have drawn there. If they were asking for that, then we'd have to incorporate the spring and the work from the atmosphere, the work from the piston, and figure out what all of those are. But they're just asking about the boundary work for air inside the cylinder. And this is going to be the work that the air does by pushing up on the bottom face of this piston here to basically resist being compressed as this piston moves downwards. So this is going to be our boundary work that we care about. And remember, we have an equation for that in our equation sheet, specifically for boundary work. So let's scroll down and look at that. So remember, this boundary work is just our PDV work. And so whenever the gas has some pressure and there's some change in volume, then we're going to have this boundary work effect, this PDV work. So this is what we are going to use. So I'll go and write that in the equations section up here. So we just have our work is going to be equal to the integral of P with respect to total volume. And this will give us an answer in joules or kilojoules like they're asking for. So how are we going to evaluate this integral? Usually in earlier parts of this exam, we'd been doing this by finding some function for pressure that includes total volume or something like that. But we don't have any polytropic process relationship here, so it might be confusing to see how we are going to relate these changes in volume and changes in pressure. It seems complicated. But I want to draw your attention to just the structure of the problem statement itself. And you might notice something strange as you do more and more practice on these exams. And what I noticed that I thought was a bit strange was that they're asking us to draw a PV diagram in the second to last part of the problem instead of the last part. Usually a PV diagram is the last thing that we do because they ask us to find all of these points and then the last thing we have to do is plot them. But they're asking for it second to last here instead of last. And maybe you haven't done enough practice to see that yet, but to me that seems a bit strange. But you might think your thermo professors are mean for writing hard exams or writing hard homework or something like that. But in this case, they're actually being really nice by leading us to the answer with an earlier part of the problem. And this is a common thing that you'll see in ME200. Even earlier in the problem, we used our answer from part B to find our answer for part C. And this is pretty typical where they will have an earlier part of the problem help you find a later part. And in this case, we can realize that our answer for part E, which is the PV diagram that we drew, will actually help us to evaluate this boundary work for part F. And the reason is that we need to think back to our calculus class and remember that we can evaluate integrals by just taking the area under a curve. And we've just drawn the PV curve on our PV diagram. So we can evaluate this work integral by just taking the area under our curve of our PV diagram. So this is our PV diagram, and to just say that and draw it out in the graph, the work from 1 to 2 will just be this area that I'm shading under the curve from 1 to 2. And this is our work integral. So if I just write that down, our work is going to be equal to the integral from V1 to V2 of pressure with respect to total volume. And we can just draw out the shapes here and evaluate them. And we have all of these properties here, so it should be easy to do the math once we just draw out the shapes. So I think the easiest way to do it is to just break it down into a triangle and a rectangle like this, and then just take the area of those shapes and then add them together. So we can just call this triangle A and this rectangle B. So this integral we can just evaluate as the area for A plus the area for B. So A just being this shaded region and B just being this shaded region here. So to write those out, we will have A is just going to be equal to our area of a triangle, which we know is 1/2 base times height. So in this case, the base is going to be this base here, which is just the difference from 0.2 to 0.5. So we'll write 1/2 times 0.5 meters cubed minus 0.2 meters cubed. And then our height is going to be this length right here, which is just the difference in pressure from state 1 to state 2. So I will write 107 kPa minus 73.2 kPa. And this got me about 5 kilojoules. And this will be in kilojoules because we're doing kilopascals. So if we instead were doing pascals, then we get our answer in just joules. And then for B, we know our area of a rectangle is just base times height or length times width or whatever you prefer. So in this case, the base is going to be the same thing, just the change in volume. So that will be 0.5 meters cubed minus 0.2 meters cubed times the height, which in this case is just going to be equal to our pressure at state 2. So that would be 73.2 kilopascals. And this is going to be equal to about 22 kilojoules. And so adding those together, we just get the work is equal to A plus B, the boundary work here. And that's just going to be about 27 kilojoules. But we need to be careful here. We might just get this answer and consider our work done, but we actually need to add a negative sign here. And the reason for that is we are going from state 1 to state 2. So we're going along this line in this direction like we drew in the arrow. And so usually when we take integrals, we take them from left to right. So like this integral here that I'm drawing would be positive. But if we're going from right to left, it's actually a negative value. So this area is going to be like a negative value because we're going from right to left. So we need to add a negative sign. And if we think about it with our problem, it makes sense because the air inside is doing work to try not to get compressed, but it's still getting compressed down, and this volume is changing from a bigger volume to a smaller volume at state 2. So this is going to be negative work that this air is doing on the piston. And so this will be our answer with a negative 27 kilojoules.